Now, in this video, we're going to look at calculating the mass of a lamina in a plane. Now, if you may recall, a lamina is essentially a thin sheet. It's so thin that we're going to neglect the height of the sheet. So we're just looking at how it's distributed in a two-dimensional plane. And we're going to do our first example in rectangular coordinates to calculate the mass of a lamina in a plane. In rectangular coordinates, we're going to do a double integral over the region defined by the boundaries of our function that bind the region. And then we're going to integrate the density over that region. So we're going to start with an example. The mass of the lamina we want to find is bounded by the curve y equals x squared and the line y equals 4. And our density function is ky. So the k is a constant, and the density is changing as y changes in this case. So our double integral is going to be bounded below by the x squared and above by 4. And then the limits in x are -2 to 2. Our density function is ky, and we're going to integrate y first and then x. So when we start doing the integration, we're going to integrate y. That's going to give us 1/2 y squared, and I pulled the k outside. And then I'm going to plug into that 1/2 y squared, both 4 and x squared. That's going to give me 16 minus x squared, x to the 4th, and I pulled the 1/2 outside with the k as a constant. And then I'm going to integrate this with respect to x. 16 will become 16x. X to the 4th will become 1/5 x to the 5th. And then I plug in 2 and -2. And this is you could also do this as an even function, since these are both even terms, and double this and integrate from 0 to 2. And make the math plugging in here a little bit easier, less confusing with all the sign changes and everything. But you should get the same answer in the end, which is 128k over 5. Notice I plugged in the 2 here to get 32, the 2 here to get 32 over 5, and then I have to subtract both of these terms, and so the signs are flipped, and plugging in -2 minus a -32, and then subtracting a negative is going to give me a positive, and plugging in -2, I will get my third negative, which survives, and 32 and 32 is 64. And -32 over 5 plus -32 over 5 is -64 over 5. And we end up with this. That is the total mass. Now, you can also do this in polar coordinates. So I have a second example. Here, we wish to find the total mass of one petal of r equals 3 cosine 2 theta. With the density unit per area given by, in this case, our density is given in polar coordinates already. If our density function was given in rectangular coordinates, we would have to do our substitutions in order to change the coordinate system that we were working in. But since this is already in terms of r, the density is getting larger as you go away from the origin. We don't have to worry about that. Now, we do have to set up our integral. The dx dy, the dA component of our double integral becomes r dr d theta. Our density function is kr. And then we have to establish where our limits of integration are. In r, we're just dealing with one petal, so we're going from 0 at the origin to this petal boundary. But where does the petal begin and end? Well, you're going to set your rho's function equal to 0, and we find that they intersect, and that makes sense here. They go back to the origin at pi over 4 and -pi over 4. So doing this symmetrically makes the math a little bit easier. You could easily do any one of these other petals, but the one in the first that is in the first quadrant or across the x-axis is very common. So those are our limits in theta. And then we just do the integration. I pulled the k out. I have r and from the density function and r from our dA. So that's r squared. Integrate that, you get 1/3 r cubed, and you plug in these two functions. We can pull out the 1/3, and then we're going to cube. 3 cubed is 27, and then cosine cubed is this. If I pull the 27 out with the k over 3, I get 9k. And then I have to pull out one of these cosines. This is the trig integration. I pull out one of these cosines, and then I convert the remaining two cosines into 1 minus sine squared with the same angle. And then I can do a substitution with sine of 2 theta, and then the derivative is 2 cosine 2 theta. And if I complete the integration with my substitution, then I will end up with, distribute this sine 2 theta, and then this becomes 1/6 sine cube theta. There's a 1/3 from the u cubed, and then there's an extra 1/2 from integrating the sine 2 theta. And then we plug in our limits, and again, you can treat this symmetrically, double it and go from 0 to pi over 4. But when you plug in the values, sine of 2 times pi over 4 is sine of pi over 2, which is going to be 1. And when you plug it in alternatively, you get negative pi over 2, which is negative 1. And you end up in the end with 6k as your total mass.